Hi, everybody. Welcome to the first part of my talk series on block encodings that I'm doing up here at the lovely Yale Quantum Institute. By the way, for those of you who are curious, that's actually a delusion refrigerator. Sorry about that. I find this kind of stuff pretty cool. But in any case, what the purpose of this talk series is to allow people to have a deeper dive into the idea of block encodings. And in particular, this is something that's really important to me, I feel, because the ideas of block encodings have really underpinned a lot of the advances that we've had in modern quantum algorithms. In particular, there's been a realization that almost all of the algorithms that we had in the past, I'd say probably about three-quarters of them at some level, were secretly hiding block encoding or the related concept of quantum signal processing or quantum singular value transformation. And these ideas are so powerful that once you understand them, many of the things that seemed like they were totally independent ideas from quantum computing are actually manifestations of a few basic concepts. And so very much like after we understood that what divide and conquer algorithms were or what dynamic programming was, these algorithm design primitives gave us new vistas of how to go forward and develop new algorithms. Similarly, these ideas have also opened up new vistas and made quantum algorithms vastly easier to understand and design. So my aim here is to give you those tools and provide a hopefully a comprehensive and understandable introduction to how we make block encodings and how we manipulate them in order to solve problems. So the goal is ultimately to be able to start off in this talk series about block encodings themselves, what they mean, what they are, why you might want to use them. And then we're going to continue forward talking about linear combination of unitaries as a way to build block encodings. Then we'll show how to use LCU and methods like quantum signal processing in order to be able to manipulate block encodings. And from there, we'll talk about how to use them to be able to do things like simulate the dynamics of quantum systems or be able to use them to actually solve differential equations, perform forms of quantum walks, basically most of the stuff that we know and love in quantum algorithms. So yeah, I hope you'll all stick around for the ride, and let's get started. So I'll begin by sharing my screen over here. Okay, cool. So block encodings. The idea of a block encoding is actually kind of old, and it boils down to the following grand message that I often tell my students. And the message is when the going gets tough, the tough go to a higher dimensional Hilbert space. Okay. So why is that? It turns out that often giving ourselves more degrees of freedom to manipulate a problem actually makes things easier. And sometimes the rate at which this ends up getting easier is entirely disproportionate to the extra memory costs that we might need. So one example that is kind of straightforward is let's consider a case where we have, say, some density operator. If we had a density operator, and the simplest one to think about here is the maximally mixed state, identity divided by 2 to the n. If we wanted to prepare this on a quantum computer, how do we do this? Well, it's difficult to be able to do this because quantum computers can't represent density operators directly. Everything needs to be a pure state preparation and unitary evolution. So it's very difficult to be able to build something like this in a direct fashion. So the easiest way of doing this is to follow this strategy and go to a bit higher dimensional Hilbert space. And in particular, we have that we can write that the purification of this density operator is 1 over root 2 to the n, sum over x, x on subsystem A, and then x on subsystem B. And basically, the idea behind this state is that what we can do is we can consider the following. If this is register A and this is register B, if we have our state psi rho, which is a purification of rho, and note here that if this density matrix is an n qubit one, this is in C 2 to the n by 2 to the n. This guy over here is in C 2 to the um, 2n up here. So the dimension is actually exactly the same between these two problems. And that's why we can end up seeing these things as being an isomorphism. And so, but in order to operationalize this input over here, what we do is we just basically say, let's trace over the B register. And in this register, we will end up getting the maximally mixed state. And more formally, what we would say is we'd say that the trace over B of psi rho is equal to identity over 2 to the n. And a quick calculation can verify that this is true. Easiest way to do it. Oh, what the heck? I'll actually just do it because it doesn't take too much time. For those of you who've seen this, feel free to fast forward. But this whole thing is going to be equal to 1 over 2 to the n, in this case, trace over the second register, and it's a maximally mixed state. So the maximally mixed state can be written as sum over xy, um, x, or I should say not the maximum mixed state. This state over here, when we expand it, can be written as the correlated sum over the x and y's on both of these registers. Now, using the linearity of trace, partial trace that is, this is equal to 1 over 2 to the n, sum over xy, partial trace over x outer producted with y on the register A, tensor producted with x outer producted with y on the B register. Now, using the definition of partial traces, this is 1 over 2 to the n, sum over xy, x outer producted with y, times the trace of x outer producted with y. Now, of course, the trace of this off-diagonal projector is 0 because, in general, if x doesn't equal y, then we'll have a matrix that's kind of like of this form over here. Okay, and so what we'll end up getting is that the trace of that of this over here is 0 because trace is just the sum of the diagonal elements that we end up getting in our matrix. So therefore, this result is just going to be 1 over 2 to the n, sum over xy, xy, Kronecker delta, xy, which is just equal to the identity divided by 2 to the n. Okay, so that shows how we can build the maximally mixed state as a piece of a larger pure state. So cool. Well, the question is, can we do the same thing also for matrices? So if I had a matrix, let's say I've got a matrix A, and what I'd like to be able to do is I'd like to be able to apply A to a state over here. Now, if A was unitary, then this is straightforward. You just build a quantum circuit that would looks like psi, put A in, and done, right? But unfortunately, not all matrices that we would like to actually work with are unitary. So if A is not unitary, then what can we do? Well, what we can do is we can follow the same inspiration that we used above with this choice state that we've got here. So the idea basically behind this approach is that what we're going to do is we're going to make what we call a block encoding. And the idea behind a block encoding is the following. A block encoding, what we want to do is we want to construct a larger unitary matrix U, such that in a block, usually taken to be the top left-hand corner, but it technically doesn't matter. We have in this block, we're gonna have the matrix, up there, divided by this alpha concept, which I'll get to later. Alpha here is a normalization constant. And so the question is, why is alpha increased, put in here? Well, it's really obvious in a way, right? Like, let's imagine that what A was is I set A to be, I don't know, 100x plus y as the matrix that I'd like to implement. So if this is the matrix that I'd like to implement, you can see immediately, wait a second, this guy is not unitary. In fact, its norm is way bigger than what we'd want. Norm A in this case is going to be approximately equal to 100. I probably should have rigged this, so I picked something I actually knew the norm of before I started. But the point is that the norm of the matrix is much larger than the norm can be for the unitary we're trying to build it in. So what we need to do is we need to build a constant inside this guy, and that constant is alpha over here, such that alpha is greater than or equal to the norm of A. If this is true, then we can share the weight of the operator between the top left-hand block and its corresponding conjugate blocks, which could be of any size, by the way. And under these circumstances, we can shift the weight around and still embed everything in a unitary. But in general, we're not going to be able to build all matrices directly in there without rescaling. And so then that's the idea. What we'd like to do is we'd like to build a rescaled version of the non-unitary matrix that we'd like to apply inside a block of our larger matrix. So there's a question about, how we exactly end up describing this. The easiest way is to use a little bit of Dirac notation over here. So if we're using Dirac notation, then what we could do is we can end up describing U over here to be equal to 0, 0, tensor A over alpha plus sum over x, y not equal to the pair 0, 0 of x, y tensor some other matrix cxy over here. So this is kind of what we mean by the question marks. These question marks are the individual operators that we're putting in all the rest of the blocks. Now, with a block encoding, the reason why we'll often put question marks, or some people will put stars in those places, is because we actually honestly don't care what's in there. We're only using this extra space to pad out the matrix and make it so that we can conveniently build the A over alpha in a top left-hand block. So that's the form of it. Now, if we're taking a look at how to construct or pick out this element of a block encoding, then we can actually end up doing so by building some operators. So the way that we end up doing this, apologies, now you can see all of my embarrassing emails. So the way that we can end up doing that is what we do is we construct a pair of projectors in this case, well, sort of projectors. What we'd like to do is we'd like to be able to focus on this up here. So the definition that we're going to make is the following. What we're going to do is we're going to say that in general, X tensor identity acting on a matrix U over here, which I'm going to write as sum over xy, the full um, uncontracted thing, or you know what, let's make it, instead of that, let's make it a sum over mu and nu of mu outer producted with nu, tensored some matrix that we have, um, C mu nu, and y tensor product with identity. We define this notation down here in the following way. This is just going to be simply equal to C x y. Okay. So what we're doing over here is you can see how we, if we use standard Dirac notation, how we would go through and compute what we actually end up meaning when we think about all of these as being operators acting on the higher dimensional space. What we end up getting is that this over here acts as a linear functional on the first part, I guess, and so does this over here. And what ends up happening is that this ends up giving us sum over mu nu x mu outer product of mu and nu and y tensor c mu nu identity. And this part over here, you can see obviously just is going to become delta x mu times delta um, nu y. And so using the properties of Kronecker delta functions, this is just equal to cxy. So we can use this notation over here to talk about how we can select a particular block to be able to contain the matrix in here. And so by convention, we usually pick the block of interest to be 0, 0. So the definition is that we say that U is a alpha um, a epsilon block encoding of a matrix A if 0 U or 0 tensor identity U times 0 tensor identity minus um, A divided by alpha, or I guess I should say, sorry, the definition I believe is this over here. If that is less than or equal to epsilon, and the dimension of 0 here is equal to 2 to the k. Okay, so often what we'll have in these situations is if we're just interested in one block, normally 1 qubit is good enough for our purposes. But in general, we could have multiple qubits that we use in order to be able to specify the location of the block. And so this definition of what a block encoding is ends up dealing with it. And you can see this definition exactly ends up matching what we're working with here. And minimally, this would be a alpha 1, 0 block encoding of A. Because you can see here that this A is actually exactly the target that we were looking at. But if I put in A plus epsilon I, then this would end up becoming a 1 plus epsilon block encoding. All right, so that is what we mean by a block encoding. Why would we potentially want to use one, or how could we? Well, let's take a look at a particular set of examples. Let's take a look at block encoding projectors. Now, this is a really important task because, in general, one of the most important things that we do in quantum computing is measure. In fact, some might even say that's the most important thing because without measurement, we gain no information about our system. However, there's many different ways that we could choose to measure a quantum system, getting different pieces of information depending on how we exactly probe it. So what we a question that might end up coming up is, well, how can we figure out how exactly we would want to end up performing such a block encoding? And to begin with, let's go forward and consider the following construction. Let's say that what I want to do is I want to um, uh, do an example where I want to find a block encoding of the projector onto 0 for a single qubit. Well, how am I going to do that? Well, the way that we can end up doing this is that we can end up doing the following. We can see that in the following circuit will produce such a block encoding. Now, we'll get to this next lecture when I talk about how to do the LCU method. But for the moment, just trust me, this is going to work out. I'll do the math to show it to you. But you'll see later how this is a particular example of a much larger idea. So what I'm going to do is I'm going to do the following. Let's do Hadamard, Z Hadamard. I'll begin with 0 up here, and I'll measure the result. And the claim is that if 0 is measured, then state at the bottom psi will get mapped to 0, 0, psi equals 0. Okay, cool. Well, let's go through and do this. And by the way, if you're familiar with circuit identities, there's a cute way that you can take a look at this and see that all this is doing is effectively measuring the bottom qubit in a clever way. But all right, so going through the math, we have that our initial state is 0 psi. We then apply the Hadamard transform to turn it into 1 over root 2, 0 psi plus 1 psi. Okay, cool. Now we're going to do the controlled Z operation, which won't do anything to this branch, but will put a phase on the other branch. So this will end up doing 1 Z psi. Okay, wonderful. So now let's apply the Hadamard transform again, and we'll get 1/2 coming out of this. We'll have 0 psi plus 1 psi plus 0 Z psi minus 1 Z psi. Okay, regrouping everything, we end up getting that this is 0 identity plus Z over 2 psi. And the other one is 1 times identity minus Z over 2 psi. Okay, and now if you like, one way we can visualize this is that what we're doing is we're creating a flag qubit at the top that's constructing sort of two different paths. One in which the qubit is 0, if it starts at 0 over here, and it ends up becoming an equal superposition of 0 and 1. We apply now Z on this branch and do nothing on the bottom one, i.e. apply identity, and then recombine them back up. And then what ends up happening is we get two outcomes here. We get one path that basically interferes with itself to produce identity plus Z, and the other one will produce identity minus Z coming out of it. So this is probably something like identity minus Z. This would be like identity plus Z coming out the other side too. But let's take a look at what these two things are. For single qubits, identity is just 1, 1 with zeros on the top, and Z is just 1, negative 1 with zeros everywhere else. When I add these two guys together, I get identity plus Z divided by 2 is just equal to 1, 0, 0, 0, which is, in Dirac notation, just the projector onto 0. Cool, right? So what does this end up meaning? That when we measure this, the measurement outcome that we end up getting will, if we measure 0, then effectively we'll have applied projector onto 0 onto our state, because this is just 0 times the projector onto 0 times psi plus 1 times the projector onto 1, all times psi. Okay, so you can see that basically that this is exactly what we're doing. This matrix that we're implementing over here is a unitary that's of the form 0 up here and a projection onto 0 plus a projection onto 1 over here, and these matrix elements we haven't worked out. And we can clearly see that, if we use the block matrix language, or if I translate this from block matrix language to ordinary language, this whole thing would be equal to the 0, 0 tensor 0, 0 plus 1, 0 tensor 1, 1, and plus some question marks that we never really worked out. Okay, so this is very clearly a block encoding. And we can see that this, in terms of block encoding language, U gives a 1, 1, 0, because there's no error here, block encoding of the projector onto 0. So we've made this cool circuit that ends up actually applying randomly either the projection onto 0 or the projection onto 1. Now let's get some context behind this and ask, okay, cool, we've worked this out, but what is the probability of success? The success probability can be found very easily. It really is just the norm of this part of the circuit in here. The probability of applying the projector onto 0 in this language is then just equal to the inner product between 0 over here. Let's just see. Yeah, 0 here, and also psi projection onto 0 times the 0 tensored the projection onto 0 psi. Okay, now just using a distributed property of the implicit tensor product that we get in Dirac notation, we end up seeing that those two multiply by each other and those two multiply by each other. These have an inner product of 1, so we can just drop them. So this is just equal to psi 0 times the inner product of 0 and 0 times the inner product of 0 and psi over here, which, of course, because this is equal to 1, is just the absolute value of the inner product between psi and 0 squared. So this is exactly the probability that you would get if you were to perform a measurement. And in fact, this is no coincidence because this circuit that we're doing here, this is an example of von Neumann's measurement model. So when von Neumann was thinking about how to, back in the day, how to operationalize what a measurement really is for a quantum system, he actually proposed a very similar idea for this. The idea was to have a meter up at the top, and this meter serves in order to interact with the system. Now, he didn't use this language at the time, but the aim is to then produce this in a state where entanglement between the meter and the physical system will result in the state of the meter being changed. So a measurement of the meter will end up actually corresponding then directly to a measurement of the physical system below. And that's exactly what we see here. We see that by block encoding this projector, that's exactly the same thing as measuring. So basically, we've got von Neumann's measurement model kind of for free coming out from this. But one of the things that is neat that we sort of don't get from von Neumann's measurement model is that there's a different sort of way of thinking about this. In this language, we're not talking about measurement as a passive process. We're instead talking about it as an active process. Measuring the 0 here, it's equivalent to performing a projection onto the state. So we can look at this as an attempt to apply a projection onto the state, and as a consequence, it will give us an outcome that tells us whether the state was successfully projected or whether it wasn't. So this shows kind of a dual way that we can think about this, and this, I find, can be kind of useful in examples involving quantum error correction. So to give an example, kind of, something that's a little bit more interesting about this, let's actually now consider something more broad. Any let pi be a projection operator, meaning that pi squared equals pi for some operator pi, which is a linear operator acting on a 2 to the n dimensional Hilbert space. Okay, cool. So pi is a projection. Now we can carry through the exact same logic that we did with z, now using a reflection operator. Then we're going to let r be a reflection operator, which is equal to identity minus 2 pi over here. Okay. And again, just to remind you what a reflection operator is a reflection operator is a linear operator acting upon a two-dimensional, 2 to the n dimensional Hilbert space such that r squared is equal to identity. Okay, cool. So for the previous example, pi was equal to 0, 0, and r would be equal to identity minus twice the projection onto 0, 0, which is equal to, well, technically minus z, which is equivalent to z. So this gives us a um, a way of thinking about the problem of implementing projectors. So let's see how this would end up working. So now, if we assume we can construct R, then we can block encode pi. So the logic behind it is exactly the same. What we do is we begin by preparing our qubit that specifies the block that we're in. We start in 0 just by convention, and we're going to want to encode this inside the 0, 0 space. We can put psi down here, but you know what? I am just going to drop that. And we're going to say that this unitary now that we are going to want to compute for this is of the form Hadamard controlled R Hadamard. Okay. And my claim is that zero tensor identity U times zero tensor identity is actually just going to be equal to pi. Meaning in this context that this forms a 1, 1, 0 block encoding of the projector pi, using the jargon that we had above for block encodings. Okay, cool. So we can see this using exactly the same reasoning that we had before. So I'll abbreviate it just a little bit. But using the block encoding notation, this is going to be Hadamard times the controlled R gate times Hadamard acting on zero tensor identity. Now applying Hadamard on zero tensor identity will end up giving us 0 tensor I, controlled rotation, 1 over root 2, 0 plus 1 tensor I, which of course will end up giving us 0 tensor I all times the controlled rotation. Oh, let's actually just do the controlled rotation instead, times 1 over Hadamard here, I guess, 1 over root 2. Controlled rotation reflection here will be 0 plus reflection acting on 1 tensored with identity over here. Oh, I'm sorry, that's actually not quite right. When we do the R is going to act as identity on the first bit, but the controlled R on the second bit is actually going to now give us R times identity, which of course is the same thing as R on this side. Okay, and there's a Hadamard here that didn't show up. Okay, so now next step, what we're going to do is we're going to act Hadamard left on this side to give us 1/2 now of 0 tensor identity plus 1 tensor identity, all times 0 tensor identity plus 1 tensor R, which ends up giving us 1/2 of identity plus R. Okay, and oh, okay, my apologies. This shouldn't be pi. This should actually be identity minus pi. And the block encoding actually that we'll end up seeing is the opposite. So anyways, when I put this in, for the reflection, then this is 1/2 identity plus identity minus 2 pi. Actually, maybe I was right. Okay. So this is going to be 1/2 of 2 identity minus 2 pi over here. This cancels, and this is just identity minus pi. Yep, cool. So we can see that this ends up producing identity minus pi, i.e. the projection onto the complement of the projector that we wanted. And the actual element that we want, similarly, will be block encoded by the other one. So what we find is when we carry out the similar calculation, we end up finding the block projector using the block encoding language, acting on the controlled rotation over here, times the similar block projector will end up giving us I. So there you have it. We end up finding that the matrix effectively ends up looking like here, U is projection onto pi, or 1 minus pi up here, and pi down there. And there's some other useless junk over here. Oh, actually, sorry, that isn't right. This would be 0 on this side. Okay, cool. So this gives you an example of how we could carry out an arbitrary example of this. And so, as an example, let's imagine what we want to do is we want to do the vertex operator from the surface code. Now, the vertex operator is a operator that ends up looking like this. Say we've got a qubit at the center here that I'm going to call qubit 0. We're going to have a cluster of neighbors around it. And what we would like to do is we'd like to measure the X operator in this. So what we'd like to do is we'd like to have some quantum state, psi, and we would like to either push this into +1 eigenstate of x1, x2, x3, x4. Or alternatively, we'd like to push this into a minus eigenstate of the same thing. Okay, so instead of thinking about this passively, like we're measuring it and we're trying to figure out whether it's in the it's a +1 eigenstate or a -1 eigenstate, we can use now the language of LCU to think about this as an attempt for us to apply a projector onto either the +1 or the -1 eigenstate. So the reflection operator that we're going to pick in this particular case is actually really simple. The reflection operator is just x1 tensor x2, tensor x3, tensor x4, which is, of course, the same thing using the standard kind of lazy convention that the subscripts, separate subscripts imply that there's a tensor product between everything. So if that's the case, then actually our circuit for block encoding this projector onto the +1 eigenstate, say, or actually, I guess technically it'll give us the -1 eigenstate, as we realized above, will be Hadamard. This up here is the ancilla qubit. And now we're going to have our actual main qubits going down here that I'll denote in the following way. This one will be 0, 1, 2, 3, and 4. Now, we only want to reflect about everything but 0. 0 doesn't come into play. So our controlled R operation then factors into this over here. Hadamard at the top. And in the event that we, from this, end up pairing this in 0, and then measured, for example, 0 being on the other side, then we would project onto the -1 eigenstate. And otherwise, we oh, actually, sorry, it's the +1 in this case. We would project onto the -1. Okay, cool. So this is actually a standard circuit that one would end up using just kind of by rote to talk about how to measure an operator through the lens of quantum error correction. But now, through the lens of block encodings, we can end up seeing that this is actually really just a circuit that ends up block encoding identity um, minus x1, x2, x3, x4. And down here, we would end up having, sorry, I think I got the signs wrong. Yeah. And that's it. So this ends up allowing us to understand what's going on in quantum error correction, kind of in a different sort of a lens. It allows us to see, well, what we're trying to do with it is we're trying to implement projectors onto the simultaneous eigenspace of a whole bunch of different operators. And the code space that we're interested in quantum error correction is just the simultaneous +1 eigenstate of all of the operators that we're looking at. So in the event that we succeed in projecting onto all the +1 eigenstates, then we're actually good. We're in the code space, and we've kind of rounded our system, which might have some small errors, into a appropriate code word. So that's an active way of looking at it. Whereas the passive or standard way of looking at it would be we measure these syndromes, and these syndromes will tell us whether an error in the state has happened or not. From this perspective, the interpretation is no, we're not actually measuring whether there's an error or not. We're pushing our state down into a state that either has a definite error or it doesn't have a definite error. Of course, these are just different interpretations. Neither one of them is kind of more right or more wrong than the other. I'm bringing them up because of the fact that this language kind of gives us a new way of looking at standard things like these measurement circuits that you would see in quantum error correction. And similarly, actually, it gives us ways of understanding other things that are beyond that. Say we have another circuit over here. This is a famous example, by the way, of a quantum state, psi and phi, over here. What we do is we do the exact same circuit, and we carry out Hadamard over here. Now, the swap is a reflection about the anti-symmetric subspace, meaning that if we ended up having two states that were of the form psi phi, and we put a minus phi psi here, this would be an example of a state that's in an anti-symmetric subspace and is clearly a -1 eigenvector of the swap operation. So the swap operation really is a reflection that's exactly of the same form. And so carrying out precisely the same logic that we had before, we can end up seeing, well, if it's a reflection about the antisymmetric subspace, then we can see, well, this means that what happens is if we define pi sim to be a projection onto the symmetric subspace, then this unitary over here can be thought of as block encoding a projection onto the symmetric space in this block times a projection onto its complement, 1 minus pi sim, in the other space, and who knows what it does over here. So from this perspective, what this circuit, known as the swap test circuit, is doing is it's block encoding these projectors. And if we succeed on it, then we project a copy of sci-fi over here into into the same state, but projected only into the symmetric subspace. Otherwise, we're going to get a projection onto the anti-symmetric subspace. And of course, the success probability for this is the projection, the expectation value of the projector onto the symmetric subspace squared. And the interesting thing about this circuit over here is that actually this property of thinking about it actively as something that's applying a projection rather than as a method for figuring out what the overlap is between two different states, because as I said before, the probability of measuring zero at the top, you can see just from the discussion that we did previously, is 1 plus the absolute value of psi phi squared divided by 2. This over here is normally why people care about the swap test, because it gives us a way of measuring the overlap between two different vectors. However, using this approach, others at Google have invented the technique called virtual distillation that gives us a way of forming a projection onto the symmetric subspace, and in turn minimizing some types of errors that could otherwise be pernicious. So this active way of thinking about a projection can actually be really useful for designing new approaches. Whereas if we had only thought about the swap test as a method for extracting an inner product between two vectors, it might not have been obvious that actually something interesting is happening to the state, and we're applying either a projection onto the symmetric or anti-symmetric state coming out of it. So this gives us a host of examples of things that we can build block encodings for. But question is, how are we going to actually build these in general? So I showed you an elementary construction. Next time, what I'm going to do is I'm going to take you through the linear combination of unitaries paradigm, which gives a way of constructively building a circuit that block encodes an arbitrary a matrix that we are interested in. And then we'll continue through that to show how those block encodings that we've constructed for arbitrary matrices can be used in order to form the bedrock of simulation methods, differential equation solvers, and, well, the majority of known quantum algorithms. Thank you very much, and I will hopefully see you all next time.